Module 5, Lecture B, Capstone Project. By the end of this lecture, you will be able to design a small Python project that addresses a defined civil engineering workflow. Implement the project using only built-in Python functions, libraries, and data structures. And evaluate the final script for correctness, readability, and engineering usefulness. Project planning. Problem definition. Defining the problem is the first key step in a civil engineering automation project. It turns a broad engineering activity into a specific task that a Python script can support, with clear inputs and outputs. The goal is not to replace professional judgment, but to streamline repeated workflows, such as reviewing notes or checking slopes. A strong definition keeps the project focused on useful engineering decisions rather than coding for its own sake. Defining a problem starts with finding the workflow pain points, where manual civil engineering tasks are slow, repetitive, or prone to mistakes. Simple automation, such as summarizing costs, checking pavement thickness, or organizing inspection data, can save time and improve accuracy. A strong problem definition clearly states the gap between the current process and the desired one, including whether the goal is better speed, consistency, error reduction, or data interpretation. A good Python project problem in civil engineering should be narrow enough for basic tools while still showing clear engineering value. Define the setting, inputs, outputs, and limits of the script, such as checking beam spans or summarizing traffic data by hour, rather than automating an entire field. The program should support engineering work, not make final decisions. And a clear problem definition guides data handling, validation, and testing. Python code. Problem definition. Use a focused civil workflow by keeping inputs and outputs clear, and evaluate ideas before starting to code. The Project Ideas list stores possible automation projects as dictionaries so they can be compared by inputs, outputs, pain points, and scope. It includes narrow projects like a pipe slope checker, which reduces manual arithmetic errors, and a traffic count summarizer, which standardizes repeated summaries. It also includes a broad structural design automation idea, but that scope is too large for a student script. Overall, the setup helps evaluate which projects are practical and impactful. This script compares 3 automation project ideas using simple criteria: clear inputs and outputs, a real pain point, and a narrow scope. Each project receives a score out of 4, and any project scoring 3 or higher is marked as a strong candidate. The script prints each score and recommendation, then highlights the highest scoring project as the best focus. Workflow requirements. Workflow requirements define what an automation must do across a civil engineering task, from initial inputs to final outputs. They describe the needed actions, decisions, checks, and reports, not just the problem being solved. Clear requirements help ensure the automation reflects real engineering practice, such as organizing inspection findings or validating earthwork quantities and flagging anomalies. When defining workflow requirements for a Python project, clearly state what data the script will use, what processing it must perform, and what output users need. This includes the expected inputs, key assumptions, and useful results, such as summaries or flagged issues. Clear engineering requirements help guide design choices and make the script practical for real project needs. When defining workflow requirements, focus on real engineering constraints and how users will actually handle data. Plan for issues like missing fields or inconsistent units, and clearly state what the tool will and will not address. A well-defined workflow specifies the inputs, processing steps, outputs, and error handling so the final tool stays reliable, focused, and useful in practice. The script reviews mock storm drain inspection records for missing required information, such as asset, date, defect, and severity. It then identifies assets with severe defects, meaning severity 3 or higher, and counts how often they occur. Finally, it prints a summary of records reviewed, data issues, workflow requirements, and assets needing follow-up, helping ensure complete data and prioritize urgent inspections. Engineering scope. Engineering scope sets clear limits for a project, turning a broad automation idea into a focused and realistic task. In civil engineering, a small Python project should support one specific part of a workflow, such as organizing data or summarizing milestones, rather than replacing an entire design process. Defining what the script will do, what it will not do, and what assumptions it depends on helps keep the project useful and manageable. A clear engineering scope keeps a civil engineering project practical, testable, and useful. It should define realistic inputs, meaningful outputs, and simple processing steps that work with Python's basic tools and data structures. Projects should focus on one manageable engineering task, such as organizing maintenance data or estimating material quantities, while avoiding overly complex or specialized areas. Engineering project scripts must be scoped to support, not replace, professional judgment. Users should be able to understand how inputs lead to outputs, and results should be limited to appropriate purposes, such as preliminary estimates or reporting, rather than final certification or full quality assurance. Clear limits are especially important in civil engineering, where software decisions can affect public safety and infrastructure. This script estimates concrete volume for rectangular items such as sidewalks and equipment pads. It uses each element's dimensions to calculate volume in cubic feet, then converts the total to cubic yards. It also checks that the element list is usable, reports the total volume and the largest element, and presents the results as preliminary planning estimates rather than final certification. Built-in implementation. Core script structure. A good civil engineering automation script should follow the engineering workflow from inputs through validation and calculations to clear output summaries. This structure makes the logic easier to understand, especially when using only Python's built-in tools. It helps turn raw project data into useful engineering results for review. Even short scripts should be organized into clear sections for tasks like collecting data, checking inputs, performing calculations, and presenting results. This can be done with well-named functions and consistent variables without advanced techniques. Separating these responsibilities makes scripts easier to debug, adapt, and trust in engineering workflows. A well-structured Python script should make its purpose, inputs, actions, and results clear. By using simple functions, conditions, loops, and file handling, a script can guide users through tasks such as checking data or organizing records. The best scripts have logic that is easy to follow, produce results that can be verified, and remain understandable after development. The script reviews drainage project records, checks that required values are present and valid, and calculates design flow for each acceptable location using the rational method. It then reports the flow in cubic feet per second and summarizes how many locations were processed. Overall, it shows a structured engineering workflow built around validation, calculation, and clear reporting. Built-in data structures. Python's built-in data structures help organize information clearly in automation scripts, including civil engineering work. Lists keep ordered values, dictionaries connect labels to related data, tuples store fixed records, and sets capture unique values. Choosing the right structure makes scripts easier to read, test, and adapt as project needs change. When writing a script, choose data structures that match the engineering task instead of forcing everything into one flat format. Dictionaries can connect items like catchments or road segments to their key details, while lists can preserve processing order. This keeps data organized, reduces mistakes such as confusing dimensions, and helps the script reflect the real structure of the problem. Using built-in data structures, such as lists, dictionaries, tuples, and sets, makes engineering scripts clearer, more portable, and easier to maintain. They help other engineers understand small projects and prototypes without specialized tools or advanced programming skills. This supports common tasks like checking, comparing, summarizing, and reporting while keeping the focus on the workflow logic. This Python script reviews drainage catchments using built-in data structures. It checks each catchment against design limits, including maximum runoff and approved pipe sizes, then summarizes the project with the total number of catchments, combined area, allowed pipe sizes, and pipe materials used. Any catchments that fail the checks are flagged in the printed report for further review. Built-in data structures. Python's built-in data structures help automation scripts manage information clearly and efficiently. Lists handle ordered sequences, tuples store fixed records, dictionaries connect labels with values, and sets track unique items. Choosing the right structure makes the data's purpose easier to understand for anyone using or reading the script. Choose data structures that match the workflow of your automation task. Use lists when records must be handled in order, dictionaries when data should be found by an identifier, and sets when you need to compare membership or uniqueness. The right choice makes scripts clearer, more efficient, and less prone to errors. Python's built-in data structures help make engineering scripts clearer, more reliable, and easier to maintain. By organizing information with dictionaries, lists, or sets, a script can better check assumptions, reduce complicated control logic, and follow the project workflow. Choosing a structure that fits the project scale turns a simple script into a more transparent and effective engineering tool. This Python script uses basic data structures to manage culvert inspection information. It stores project details, culvert records, condition ratings, and submitted forms, then compares expected and submitted forms to find missing data. It also totals the culvert lengths and creates a status summary for each culvert, marking any unrated items as not rated. The final output gives a concise inspection overview, including location, number reviewed, total pipe length, missing forms, and condition status. Script review. Technical validation. Technical validation checks that an engineering script produces accurate, appropriate results, not just that it runs without errors. In civil engineering, this means confirming that inputs, units, coordinates, elevations, and project conditions are handled correctly. A script should be tested against simple hand calculations or other transparent checks before being trusted on larger work. Validation begins by defining the script's purpose, expected data, reasonable results, and how those results can be verified. To validate a script, test it with normal inputs, edge cases, and problematic data. This helps reveal hidden issues such as empty files, negative values, or blank entries being treated as real data. Compare the results with known examples or manual checks to make sure the script is applying the intended logic, not just producing numbers that look reasonable. Technical validation ensures a script's results can be traced back to the right inputs and processing steps. Reviewers should confirm that units, rounding, and key data are handled correctly, without hidden assumptions. Because errors can affect cost and safety, validation should be ongoing and tested against real scenarios and trusted results, so the script supports reliable professional judgment. This script validates footing volume calculations by testing a simple volume function against expected results. It checks valid dimensions, reports whether each result passes within a small tolerance, and also tests a negative depth to confirm invalid input is rejected safely. The final summary shows how many cases were checked and flags any mismatches or expected failures. Code clarity. Clear automation scripts are easier to review, reuse, and maintain after they are created. In civil engineering, this matters because scripts can affect drawings, quantities, and inspections. Meaningful names and a logical structure help reviewers understand the script's purpose, assumptions, inputs, calculations, and outputs, making the automated workflow easier to trust and follow. Use comments and documentation to explain the reasoning and engineering assumptions behind a script, not to repeat what the code already shows. Clarify choices such as filtering data fragments or rounding quantities, but avoid excessive comments that create confusion. A good test is whether a junior engineer familiar with the project can understand the logic and assumptions without needing much extra explanation. Clear code is not just about appearance. It helps prevent errors and supports good engineering practice. Well-structured scripts are easier to test, debug, update, and reuse as project needs change. Clear prompts and consistent outputs also help team members apply scripts correctly. The goal is to make the logic transparent so others can verify, maintain, and trust the script in real workflows. This script checks whether drainage pipes meet a minimum slope requirement. For each pipe, it uses the pipe's length and drop to calculate the slope percentage, then marks the pipe as acceptable if the slope is at least 1%, or flags it for review if it is lower. It prints a concise summary of each pipe's result and reports how many pipes need further engineering review. Engineering usefulness. A script is useful in engineering only as it supports real work, not just if it runs correctly. Good automation should reduce effort, improve consistency, or help prevent errors in tasks such as calculations, data organization, or measurement checks. Its value depends on how clearly it solves a practical need and supports sound engineering judgment. A useful engineering script should fit smoothly into the workflow, use familiar inputs, and turn data into clear, actionable results. It should save time, make checking and comparison easier, and reduce common mistakes, such as transcription errors or unit inconsistencies. The best scripts also state their limits clearly, so users are warned about missing data, assumptions, or results that could be misleading. When reviewing the script, check whether it works beyond a single test case and can handle reasonable variations within its purpose. It does not need to be a full application, but it should manage different inputs, incomplete data, or multiple records when relevant. A strong script is clear, practical, and useful for summarizing information, improving reliability, and making engineering tasks more efficient. This script reviews culvert inspection records to find assets that need engineering attention. It skips records without a rating, tracks usable and incomplete data, and flags culverts with low ratings or debris as priorities. It also calculates the average length of the checked culverts and reports whether the available data is strong enough to support decision-making. In this lecture, you learned to Design a small Python project that addresses a defined civil engineering workflow. Implement the project using only built-in Python functions, libraries, and data structures. And evaluate the final script for correctness, readability, and engineering usefulness. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.